Hello guys, welcome to my video again. So in the second video of today, I'm going to show you what's um, added to the software release 2.1.1 alpha. Okay, so the reason I changed the software release version to alpha is because uh, in this software update, I changed a lot of code to accommodate the fix for ultralinear connection, and those changes are everywhere. So I think the possibility that there's a bug somewhere is quite high. So and that's why I did another formal release, the software version 2.0, because I think most of the users will be happy with the stable version of software, and it will be quite frustrating if I upload this new software with lots of bugs. So now that's why I supply two versions of software, one stable release for the production for regular users, and the alpha, the trial release for adventurous users. Okay, so in this 2.1.1 alpha release, I majorly fix the test mode for ultralinear topology. So before we run the software, let's have a look at what's ultralinear topology. Okay, so this is probably not new for you guys. Ultralinear topology is here I use a 6L6 as the output tube, and this is the output stage for amplifier. There's a output transformer used. Okay, and the primary winding of the transformer has a separate winding for the screen electrode. Okay, and this is how we can assume the signal will be connected using, if the signal is generated from etracer, we connect the screen voltage. We connect HV to this to the screen electrode, and we connect the HV onto the plate, and we use -V to supply test the sweep signal. Okay, so this kind of topology is dated back to the 30s. It was invented by Adam Brunline, a very famous engineer in UK in 1977. He patented this circuit in 1937 in UK, and later in US in 1938. Okay, in the 50s, David Heffler and Herbert Keros found the ultralinear region in this topology, and in this region, the high-level distortion is minimal, and a lot of merit for this kind of topology. So it can be illustrated in this figure. So okay, so let's come back to the this figure again. So the in the primary winding, if this ultralinear tap is very close to the where the system voltage the high voltage is connected, then the operation will be very close to the pinto connection. And well, if the tap is very close, or is very close to the plate, the operation will be identical to the triad connected output tube. So basically, the ultralinear topology, we expect the behavior will be between a pentode connected triad to a triad connected pentode. Pentode connected pentode. A pentode connected under pentode mode, or a pentode connected under triad connection. So here we can see with different winding percentage, the circuit can be on the one extreme it's very close to a triad, and on the another extreme it's close to a pentode. And the green line is the maximum power output. So the closer to the triad mode, the lower the output power. High level distortion is represented by the red line. So as a triad, in triad mode, the higher the output power, the higher the high level distortion. And the purple line is the low level distortion. So when the signal level is low, the triad has a better linearity, so hence the distortion is lower. Okay, and the blue line is the internal impedance. Is okay. So as we all know, the triad has a very low internal impedance, while pentode mode has a very high internal impedance. And what David and Herbert found is we seeing a very narrow region with a certain percentage of winding, the tap for the winding. There is a region represented by this yellow band where the output power is very close to a pentode, is high, and the impedance is quite low compared to the pentode mode, and the high level distortion is low, and also the low level distortion is also lower than the tube operating under pentode mode. So this, and they give the this spatial region a name, the ultralinear region, the ultralinear operation. And this region is different tube by tube. So different type of output tube, you need to select a different winding percentage, different percentage of the tap for the screen electrode. Okay, and personally, I doubt the even it's the same tube, probably different tube, even the same type might require different, might have a different ultralinear region. Okay, so the above the document can be found in this article in Ultralinear Amplifier, published in 1951. Okay, so with this figure, so if we assume the loss in the transformer, the copper loss, those kind of stuff is 0, then we can see when because B plus is fixed voltage, so under fixed bias condition, HV2 and HV1 or plate and the screen share the same voltage. And when there is a signal swing on the grid, the HV2, the voltage of HV2 will be set by the voltage on HV1 with a percentage with a scaling factor. So in other words, the voltage on HV2 has a DC component which equals to B2, and the AC component which is a factor of the AC component on HV1, and so that scaling factor, I called it the linkage vector in my code. So the update formula can be written in this way: the voltage applied on HV2 equals to VB, the DC voltage, the high voltage, B plus voltage, plus the the K is a linkage factor, and times the HV1 minus VB. HV1 minus VB is AC component on the plate. So we can experiment. We can plug in K with two extreme values. So if K equals to 0, then HV2 equals to B. That means the tube is tested under pentode mode. The screen is connected with a fixed voltage. When K equals to 1, and HV2 will equals to HV1 because AVB will be cancelled out by this VB term here. So HV2 equals to HV1, so it means the operation is identical to a triad. Okay, so with a K in the very in between 0 and 1, we have a different the AC component on HV2 is set accordingly. Okay, so that's it. So in previous release, I didn't consider the AC component of the signal. So so that's why I only supply the one entry box for the if HV2 link HV1 is checked, and the HV2, the output on HV2 will be a linear scaled value of HV1. Okay, but it's done wrong. We need to separate the DC component and the AC component. So okay, let's use the 6L6 for as an example. UL test. Okay, so for ultralinear test, ultralinear mode is only valid under the full scan tab. Okay, now this one. So here I already have the configuration file for the ultralinear for this for a 6L6 connected under ultralinear mode. So the configuration is pretty similar to other configuration. The connection is the same, and so here HV1 is a usual has a usual swing from 0 to 500 volt. HV2 is enabled and link to HV1. So the HV2, the voltage on HV2 follows HV1 in a certain way, and the negative voltage supply supplies the signal swing. So its sweep is checked and start from 0 volt to minus 40 volt, and we see a step of minus 4 volt. So let's turn on the heater. Okay, and so when the link HV1 is checked, we can set the type of linkage for HV2. So we have two choices: linear. So under linear, the HV2 is a direct scaled value of HV1. For example, if HV1 is 100 volt and we set the linkage to 90%, the HV2 will be 90 volt. Okay, so here if we check this box, then the linkage type will be following this formula. Okay, so here we need to enter the DC, the high voltage B plus value. Here I enter 300 volt, and we can decide the linkage value. Okay, and let's say we use 50. Okay, so with this configuration, we start scanning, and the HV2 will follow this formula, and K will be 0.5. And now we can see the curves with the plate current marked in red, and the screen current marked in green. Okay. Okay. So once we get this graph, how do we interpret the measurement result? Okay. So I think at least we can get the because we can get the current reading on the plate and the screen, so we can learn the power dissipation on those two electrodes, and we can make sure there's the power dissipation on the screen, especially on the screen electrode, doesn't exceed the design maximum of the appeared in the tube data sheet. And however, there's further analysis. I think it's not possible as people might expect, because people might expect to use this major data to do a low line analysis. I think it's not possible, or at least it's not accurate. The reason is because the load, the primary inductance of the inductance of primary winding of the output transformer is distributed on both the electrode, the screen electrode, and the plate electrode. So we cannot write the load in a closed form, and so because of that, we cannot run a single straight low line and perform the low line analysis and derive the output signal, the voltage swing, the distortion, that kind of stuff. So that's not possible. Okay, so the scan is done, and that concludes my presentation for this video. And again, Merry Christmas, and enjoy your holidays. I'll see you next time. Bye.